In the movies, time travel is easy. You step into a modified DeLorean, punch in a date, and step out into 1955. But the actual physics of time travel are far more complex than anything Hollywood has put on screen. Most of us experience time as a strict, universal metronome, a steady flow where a second on Earth matches a second in deep space. Modern physics defines time as the fourth dimension, woven into space to create spacetime. This unified grid is a physical fabric that can stretch and bend. Therefore, time travel is a mathematical reality built into our universe. However, as scientists have discovered, while the universe allows for movement through time, it currently only issues one-way tickets. In 1905, Albert Einstein proposed his theory of special relativity, which demonstrated that our perception of a rigid timeline was an illusion. He introduced the concept of time dilation. The rule is highly counterintuitive. The faster you move through space, the slower you move through time relative to everything else. This timeline comparison shows the scale of the effect. If an astronaut travels at 99.99% the speed of light for 5 years, they would return home to find that hundreds of years have passed on Earth's timeline. Velocity is only half the equation. Intense gravity also warps the fabric of space-time, acting as a physical drag that slows the passage of time. Near a supermassive black hole, gravity is so strong that time slows to a crawl. Spending just a single hour in orbit near that kind of gravitational pull means decades or even centuries could pass for the rest of the universe. We have already verified this effect using atomic clocks on commercial airplanes. When those planes landed, their clocks had ticked slightly slower than identical clocks left stationary on the ground. This is a factor in our daily technology. GPS satellites orbit in a different gravitational and velocity environment than our phones. Without calculating and correcting for time dilation, global navigation systems would fail by several kilometers every day. Traveling into the future is a proving physical phenomenon. It is an active engineering reality that dictates how our satellites function and how our universe operates. If the laws of physics encourage us to move into the future, why does the universe seemingly block us from traveling backward into the past? The only physical mechanism physicists have hypothesized for backward travel is a wormhole. As visualized here, a wormhole is a theoretical tunnel that folds space-time to connect two distinct points. However, these tunnels exist only in mathematical models. No stable wormhole has ever been discovered in nature, and we have no evidence that they can physically form. Even if we could stabilize one, backward travel creates severe logical contradictions, most notably the grandfather paradox. As this timeline shows, moving backward to a point before your own birth creates an impossible loop. If you prevent your grandparents from meeting, your parents are never born, meaning you never exist to travel back in the first place. Some quantum theories suggest a potential solution: parallel universes. Instead of creating a paradox on a single timeline, traveling backward might cause the universe to split, allowing history to play out differently in an alternate branch. But it is important to note that this parallel universe hypothesis currently has zero experimental proof. While the mathematics of spacetime leave a theoretical opening for backward travel, logical contradictions and a total lack of physical evidence keep it firmly in the realm of speculation. The scientific verdict is clear. Moving into the future is a tested reality, while moving into the past remains unsupported by evidence. This process doesn't rely on cinematic machines, but on the physical mechanics of velocity and gravity. While we cannot revisit previous events, our universe provides the mechanical capability to jump forward and experience a future Earth. Until we discover new laws within quantum mechanics, the deep future remains the only destination our science says we can truly reach. Knowing how these physics work, if you had a ship fast enough to reach the future, how far would you go, and what would you hope to find when you arrived?